On August 17, 2024, the James Webb Space Telescope detected catastrophic thermal emissions from Saturn's upper atmosphere, 427 Kelvin, in layers that should be minus 180 degrees Celsius. The readings triggered emergency NASA consultations and requests for classified briefings. The data revealed processes so violent and chemically anomalous, they defy conventional planetary physics, energy signatures that mirror stellar reactions, not weather patterns. What if Saturn is concealing atmospheric phenomena that could fundamentally transform the planet within our lifetimes? What if the mysterious heat source isn't releasing energy, but triggering a planetary-scale reaction? What if James Webb didn't detect weather at all, but something far more disturbing? The data is undeniable. The implications are staggering. The fear among researchers is palpable. Prepare yourselves. We begin. The initial detection came not from a targeted observation of Saturn, but from background calibration data that wasn't supposed to show anything unusual at all. James Webb had been conducting routine sensitivity checks on its mid-infrared instrument, using Saturn as a calibration target because the planet's thermal emissions were considered well-characterized and predictable from decades of previous observations. The technician who first noticed the anomaly, Dr. Rebecca Torres at the Space Telescope Science Institute in Baltimore, initially assumed the data represented instrumental malfunction. Calibration targets aren't supposed to surprise you, but the anomaly persisted through 3 separate observation sequences, taken over 48 hours. The thermal excess wasn't random noise or detector artifact, and it was real, it was enormous, and it was localized to a specific atmospheric region at Saturn's equator, spanning approximately 15,000 kilometers in longitude. That's roughly the diameter of Earth. Something in Saturn's atmosphere was generating heat equivalent to the total energy output of 40 million terrestrial volcanic eruptions, occurring simultaneously in a region the size of our entire planet. The spectroscopic signature of the heat source defies conventional atmospheric chemistry. When JWST's instruments analyzed the specific wavelengths of infrared radiation emerging from the anomalous region, they detected emission lines corresponding to molecular species that should not exist in Saturn's upper atmosphere. Tricarbon molecules, linear chains of 3 carbon atoms denoted as C3, appeared with concentrations 847 times higher than equilibrium chemistry predicts. These molecules form only at temperatures exceeding 1,000 Kelvin and are immediately destroyed by photochemical reactions with hydrogen. Their presence indicates ongoing production processes operating far more energetically than solar ultraviolet radiation could drive. The spatial resolution of JWST's infrared camera revealed structure within the thermal anomaly that appears inconsistent with natural atmospheric circulation. The hot region shows a hexagonal boundary with vertices positioned at precisely 60-degree intervals around a central maximum. Natural atmospheric phenomena on rotating planets typically produce circular or elliptical features due to Coriolis effects and pressure gradient forces. Hexagonal structures require standing wave patterns with specific wavelength relationships that are extraordinarily rare in fluid dynamics. The only other hexagonal atmospheric feature ever observed is Saturn's North Polar Hexagon, discovered by Voyager and monitored for 4 decades. The appearance of a second, much larger hexagonal structure at the equator suggests either an unknown atmospheric dynamics mechanism or the presence of organized energy released from below. Dr. Lee Fletcher at the University of Leicester, who has spent 15 years studying Saturn's atmospheric composition, stated in an internal communication that was later leaked to the scientific community. The energy budget doesn't close. We're detecting thermal emissions that require power sources equivalent to Saturn's entire internal heat flux, concentrated in 0.2% of the planet's surface area. There is no known meteorological or geological process that can produce this degree of energy localization. The leaked memo continued with a single sentence that sent shockwaves through the planetary science community. We may be observing the onset of a runaway atmospheric instability. The concept of runaway atmospheric instability on a gas giant planet had been theoretical speculation until this detection. The scenario involves positive feedback loops, where atmospheric heating drives circulation patterns that concentrate additional heating, which drives more intense circulation, creating exponentially accelerating energy release. On terrestrial planets, such runaways are limited by the finite reservoir of volatile materials and the solid surface that eventually radiates excess heat to space. On gas giants with no solid surface and essentially unlimited volatile reservoirs, theoretical models suggest that runaway instabilities could propagate throughout the entire atmosphere, fundamentally transforming the planet's structure within timescales measured in mere decades. The chemical composition analysis reveals that the atmospheric region isn't just hot. It's chemically active in ways that parallel stellar atmospheres rather than planetary ones. JWST detected emission lines from ionized molecular hydrogen, which requires temperatures exceeding 2000 Kelvin or intense radiation fields, far beyond what solar ultraviolet can provide. The ionization fraction measured at 0.03%, meaning 3 out of every 10,000 hydrogen molecules in the affected region have lost electrons, indicates energy densities typically associated with stellar chromospheres, the superheated layers above a star's visible surface. Saturn's atmosphere is exhibiting stellar-like behavior, despite being a planet with core temperatures far below fusion ignition thresholds. The temporal evolution of the phenomenon provides the most disturbing evidence that we're observing something unprecedented. When researchers compiled archival infrared observations from ground-based telescopes, the Spitzer Space Telescope, and Cassini's CIRS instrument spanning back to 2004, they discovered that the thermal anomaly has been gradually intensifying for at least 20 years. In 2004, the excess temperature in this region was barely detectable, perhaps 15 Kelvin above background. By 2017, when Cassini made its final measurements, the excess had grown to 73 Kelvin. Now, in 2024, JWST measures an excess of 607 Kelvin and rising. The heating is accelerating exponentially, with a doubling time that has decreased from 8 years to just over 3 years. If this acceleration continues at its current rate, projections show the affected atmospheric region will reach temperatures of 2,400 Kelvin within 7 years. At these temperatures, molecular hydrogen begins dissociating into atomic hydrogen, releasing enormous quantities of energy through the bond-breaking process. The dissociation of molecular hydrogen in Saturn's massive atmosphere could trigger cascading reactions that spread to adjacent regions, potentially consuming the entire planetary atmosphere in a runaway dissociation event. This scenario, while still considered low probability by most researchers, would transform Saturn from a hydrogen-dominated gas giant into something resembling a brown dwarf star, glowing with thermal and chemical energy from ongoing atmospheric reactions. The magnetic field measurements from Cassini's final orbits through Saturn's inner magnetosphere in 2017 now take on sinister significance when re-examined in light of JWST's thermal detection. Cassini detected localized magnetic anomalies at Saturn's equator, regions where the magnetic field strength varied by up to 3% from the predicted dipole configuration. These anomalies were dismissed at the time as minor perturbations from atmospheric currents conducting electricity through ionized gases. But the spatial correspondence between the 2017 magnetic anomalies and the 2024 thermal anomaly detected by JWST is exact to within the measurement precision of both instruments. This correlation suggests that electrical currents of staggering magnitude, potentially exceeding 10 million amperes, are flowing through the affected atmospheric region. The energy source driving such enormous electrical currents remains unidentified, and this represents perhaps the most frightening aspect of the entire phenomenon. Saturn's internal heat source has been attributed to ongoing gravitational contraction of the planet and precipitation of helium droplets in the deep interior, processes that release approximately 2 × 10 to the power of 17 watts of power. This internal heat flux has remained stable for billions of years and shows no evidence of variation. Yet, the thermal anomaly detected by JWST requires an additional power input of at least 8 times 10 to the power of 16 watts localized to a small equatorial region. Where is this energy coming from? What process could suddenly activate after billions of years of stability and begin pumping planetary-scale power into a localized atmospheric region? Dr. Amy Simon at NASA's Goddard Space Flight Center, principal investigator for JWST's Saturn observation program, authorized an emergency proposal for 120 additional hours of telescope time dedicated to continuous monitoring of the thermal anomaly. The proposal, submitted on September 3, 2024, contained language rarely seen in observational astronomy requests. The phenomenon under investigation may represent an existential threat to the structural integrity of Saturn's atmosphere. Continuous monitoring is required to establish whether the observed acceleration continues, stabilizes, or enters runaway mode. Time is critical. The proposal was approved within 48 hours, unprecedented speed for the typically months-long review process, indicating that NASA's senior leadership shares the concern about what's happening at Saturn. The spectral analysis of molecules in the affected region reveals chemical compositions that challenge fundamental assumptions about gas giant atmospheric chemistry. In addition to the tricarbon molecules, JWST detected polycyclic aromatic hydrocarbons with molecular weights exceeding 500 atomic mass units. These complex carbon structures form through high-temperature synthesis reactions that require both extreme heat and specific pressure conditions. On Earth, similar molecules form in combustion processes and in the atmospheres of carbon-rich stars. Their presence in Saturn's atmosphere suggests that carbon atoms are being stripped from methane molecules and reassembled into progressively larger and more complex structures through processes that parallel industrial carbon nanotube synthesis rather than natural planetary chemistry. The atmospheric dynamics models, attempting to explain the hexagonal structure of the thermal anomaly, have produced results that deeply disturb the researchers running the simulations. Dr. Kunio Sayanagi at Hampton University developed a high-resolution atmospheric circulation model, incorporating the observed heat source and molecular concentrations. When the model was run forward in time from current conditions, it showed the hexagonal structure expanding and intensifying, developing internal vortices with wind speeds exceeding 800 meters per second, twice the speed of sound in Saturn's hydrogen atmosphere. These supersonic vortices create shock waves that heat the surrounding gas, feeding additional energy into the system and driving further acceleration. The model predicts that within 12 years, the hexagonal structure will have grown to encompass Saturn's entire equatorial region, creating a permanent band of superheated, chemically anomalous atmosphere girdling the planet. But the truly terrifying results emerged when Dr. Sayanagi extended the simulation to longer timescales. By year 35 of the simulation, the equatorial heat band had destabilized Saturn's global circulation patterns, shutting down the jet streams that normally transport heat from equator to poles. Without this heat transport, the equatorial regions continued heating, while polar regions cooled, creating unprecedented temperature gradients. By year 50, the simulation showed the equatorial atmospheric temperature exceeding 3,200 Kelvin, hot enough to begin ionizing helium atoms and create a permanent plasma layer. At this point, the simulation crashed as the atmospheric physics equations reached conditions beyond their validated parameter ranges. The model had pushed Saturn into a thermal regime where the distinction between planet and star begins to blur. The radiation environment around Saturn is changing in ways that correlate with the atmospheric anomaly, and this has profound implications for the planet's extensive moon system. The Hubble Space Telescope's Space Telescope Imaging spectrograph detected a 340% increase in ultraviolet emissions from Saturn's equatorial region compared to measurements taken in 2019. This UV radiation originates from electronic transitions in highly excited molecular hydrogen, molecules that have absorbed so much energy that their electrons orbit in quantum states far above the ground state. When these excited electrons drop back to lower energy levels, they emit ultraviolet photons. The dramatic increase in UV emission indicates that the atmospheric heating is being accompanied by intense molecular excitation processes that flood the surrounding space with high-energy radiation. Saturn's inner moons, Mimas, Enceladus, Tethys, Dione, and Rhea, orbit within the radiation belt surrounding the planet, and they're now being exposed to UV flux levels, 3.4 times higher than historical norms. For Enceladus, this increased radiation could have catastrophic consequences. The moon's south polar geysers eject water vapor and organic molecules from the subsurface ocean, creating a faint atmosphere and feeding material into Saturn's E-ring. The increased UV radiation will break down these molecules far more rapidly than before, potentially destroying organic chemistry in the plume before it can be analyzed by future missions. If the radiation levels continue increasing, they could sterilize Enceladus's surface and plume environment, eliminating one of the solar system's most promising locations for finding extraterrestrial life. The magnetic field interactions between Saturn and its moons are being disrupted by the atmospheric anomaly in ways that appear to threaten the long-term orbital stability of the inner satellite system. The electrical currents flowing through the anomalous region generate magnetic fields that add to Saturn's primary dipole field, creating a complex multipole configuration that varies with the planet's rotation period. As moons like Enceladus and Dione orbit through these time-varying magnetic fields, they experience electromagnetic forces that slightly alter their orbital velocities. Over decades to centuries, these small perturbations could accumulate, shifting orbital periods and potentially destabilizing the precise resonances that have kept the inner moon's orbits stable for billions of years. Orbital instability could lead to moon-moon close encounters, ejections from the Saturn system, or even collisions, outcomes that would fundamentally reshape the architecture of Saturn's satellite system. The observational campaign to monitor the phenomenon has revealed variations on timescales of hours that suggest the atmospheric instability may be more dynamic and unpredictable than initial analysis indicated. On October 12, 2024, during a 14-hour continuous observation sequence, NIJWST detected a thermal flare where temperatures in a 2,000-kilometer region suddenly spiked to 892 Kelvin, nearly double the background anomaly temperature, before declining back to baseline over a 6-hour period. The flare was accompanied by a burst of radio emissions at frequencies between 10 and 40 kilohertz, detected by the ground-based low-frequency array telescope in the Netherlands. Radio emissions at these frequencies come from electron-cyclotron master instabilities in magnetized plasmas, the same mechanism that produces Earth's auroral kilometric radiation. The detection of such radio bursts from Saturn's equator, thousands of kilometers from the auroral zones at the poles, indicates that the atmospheric anomaly is generating its own localized magnetized plasma regions. The chemistry of these plasma regions appears to be producing materials that should not exist in planetary atmospheres. High-resolution spectroscopy during the thermal flare detected emission lines from magnesium ions, atoms of magnesium that have lost 2 electrons. Magnesium is not a significant component of Saturn's atmosphere, existing only as trace contamination from meteoroid ablation. The detection of ionized magnesium requires not only temperatures exceeding 2,500 Kelvin, but also the presence of elemental magnesium in concentrations far higher than background levels. The implication is that the thermal anomaly is somehow concentrating and vaporizing solid materials, possibly meteoroids or particles from Saturn's rings that have fallen into the atmosphere, and processing them into ionized plasmas. This material processing capability raises a disturbing question. Could the atmospheric anomaly be consuming Saturn's rings? The D-ring, Saturn's innermost ring component, orbits just above the cloud tops and continuously loses material to atmospheric drag. Particles spiral inward and eventually plunge into the upper atmosphere, vaporizing as they fall. Under normal conditions, this ring material adds negligible mass and energy to Saturn's atmosphere. But if the thermal anomaly creates localized regions of low atmospheric density through intense heating and updrafts, it could actually enhance the rate of ring particle infall by reducing drag at higher altitudes and allowing particles to penetrate deeper before vaporizing. Enhanced particle infall would deliver both mass and orbital kinetic energy to the anomalous region, potentially providing an additional energy source that accelerates the instability. The Cassini spacecraft's final observations during its grand finale orbits in 2017 detected D-ring particles falling into Saturn's atmosphere at a rate of approximately 10,000 kilograms per second. If the thermal anomaly has increased this infall rate by even a factor of 2, the additional kinetic energy deposited equals 4 times 10 to the power of 14 watts. Not enough to fully explain the thermal anomaly, but significant enough to contribute to sustaining it. This creates a feedback loop. The thermal anomaly enhances ring particle infall. The kinetic energy from falling particles adds heat to the anomaly. The increased heating further enhances particle infall. Such feedback loops are characteristic of runaway processes that can accelerate without limit until some external factor intervenes to shut them down. What external factor could possibly shut down a planetary-scale atmospheric instability on Saturn? The planet has no solid surface to absorb excess heat, no magnetic field configuration that could divert energy flows, an atmospheric mass so enormous that no chemical depletion could occur on timescales less than millions of years. The only natural shutdown mechanism would be radiative cooling. If the anomalous region became hot enough, it would radiate energy to space faster than internal processes could generate it, reaching a steady state at some elevated temperature. But the current observations show no signs of approaching such equilibrium. The acceleration is continuing, perhaps even intensifying. The worst-case scenario that keeps planetary scientists awake at night involves the thermal runaway penetrating deep enough to reach Saturn's metallic hydrogen layer. At pressures exceeding 2 million Earth atmospheres and temperatures above 10,000 Kelvin, conditions that exist approximately 30,000 kilometers below Saturn's visible cloud tops, hydrogen transforms into a metallic fluid that conducts electricity. The metallic hydrogen layer extends from this depth down to Saturn's rocky core, constituting approximately 60% of the planet's mass. If the atmospheric instability propagates to these depths, it could disrupt the convective motions in the metallic hydrogen that generates Saturn's magnetic field. Magnetic field disruption would allow the solar wind to penetrate deeper into Saturn's magnetosphere, delivering additional energy to the already unstable atmosphere and potentially triggering even more catastrophic reactions. The historical precedent that researchers keep referencing, despite its controversial status, is the Great White Spot phenomenon that erupts in Saturn's atmosphere approximately every 30 Earth years. These massive storm systems appear suddenly, grow to encompass areas larger than Earth, and persist for months before gradually dissipating. The storms show thermal signatures, complex chemistry, and magnetic field disturbances, similar in character, though not in magnitude, to the current anomaly. But the great white spots always dissipate. They reach a maximum size and intensity, then fade as their energy sources exhaust, or atmospheric dynamics disperses the stored energy. The current anomaly has already persisted longer and grown larger than the most extreme great white spot ever observed, and it shows no signs of dissipating. This suggests we're observing not a normal storm system, but something qualitatively different. A new mode of atmospheric behavior that Saturn has never exhibited during the decades we've monitored it. Dr. Imke de Pater at the University of California, Berkeley, whose radio observations of Saturn span 40 years, made a statement in a closed session at the October 2024 Division for Planetary Sciences meeting that was reported by attendees to have visibly disturbed the audience. What we're seeing is not weather. Weather is a transient response to energy imbalances that self-regulates through redistribution and radiation. This is exhibiting positive feedback acceleration characteristic of phase transitions. We may be watching Saturn undergo a transition from one stable state to another, and we have no idea what the final state will look like. The concept of planetary phase transitions, where a planet's entire structure and behavior shifts from one stable configuration to another, exists mainly in theoretical astrophysics applied to gas giants migrating inward toward their parent stars. Such hot Jupiters are heated by stellar radiation to temperatures where their atmospheres expand dramatically and may even undergo hydrodynamic escape, losing mass to space. But Saturn orbits far from the Sun in the cold outer solar system, where stellar heating is negligible. What could trigger a phase transition in Saturn's structure now, after 4.6 billion years of stability? The answer might lie in Saturn's ongoing evolution through gradual gravitational contraction. Gas giant planets convert gravitational potential energy into thermal energy as they slowly contract under their own gravity, gradually shrinking in radius by approximately 1 millimeter per year. This contraction has continued throughout Saturn's history and will continue for billions of years more. However, theoretical models show that such contraction may not be perfectly smooth. At certain critical densities, phase transitions in hydrogen or helium in the deep interior could release sudden bursts of gravitational energy, temporarily increasing the internal heat flux. If the current atmospheric anomaly resulted from such a phase transition event in Saturn's deep interior, now the energy release could continue for decades or even centuries before the interior structure restabilizes. The spectroscopic detection of deuterium enrichment in the anomalous region adds another layer of mystery to the phenomenon. Deuterium, heavy hydrogen with one proton and one neutron rather than just a single proton, exists in Saturn's atmosphere at a ratio of approximately 2 deuterium atoms per 100,000 normal hydrogen atoms. But JWST's high-resolution spectrographs detected deuterium enrichment in the thermal anomaly, reaching 3.7 deuterium atoms per 100,000 hydrogen atoms, an 85% increase over the background level. This enrichment cannot be explained by known atmospheric chemistry or dynamics. On Earth, deuterium enrichment occurs when lighter hydrogen preferentially escapes to space, concentrating the heavy isotope. But Saturn's gravity is far too strong for atmospheric escape to significantly fractionate isotopes. The enrichment must result from some process occurring within the anomalous region itself, possibly related to the extreme temperatures and chemical reactions that characterize the phenomenon. The timeline for potential catastrophic outcomes remains highly uncertain, but researchers have attempted to bracket the possibilities using different modeling approaches. The most optimistic scenario, proposed by Dr. Lee Fletcher's group, suggests the thermal anomaly might stabilize at its current energy level and persist indefinitely as a permanent equatorial feature, analogous to Jupiter's Great Red Spot. This scenario requires that some currently unknown energy dissipation mechanism will activate and balance the heating, preventing further temperature increase. The moderate scenario, considered most probable by approximately 60% of researchers surveyed at the October DPS meeting, predicts continued exponential growth for another 5 to 12 years, followed by a rapid expansion phase, where the anomaly engulfs Saturn's entire equatorial zone within months. The worst-case scenario, considered low probability but not impossible, involves thermal runaway, penetrating to the metallic hydrogen layer within 15 to 20 years, disrupting Saturn's magnetic field and potentially triggering catastrophic magnetic reconnection events that inject enormous additional energy into the atmosphere. Then none of these scenarios involve Saturn suddenly exploding or transforming into a star, outcomes prohibited by fundamental physics, since Saturn's mass is approximately 80 times too small to ignite hydrogen fusion. But even the moderate scenarios would transform Saturn from the serene, photogenic planet with beautiful rings into a turbulent, energetically violent world, surrounded by energetic radiation belts that could threaten spacecraft and disrupt its moon's environments. The rings themselves, the defining aesthetic feature that makes Saturn humanity's favorite planet, might gradually disappear as enhanced particle infall feeds the atmospheric instability, while radiation pressure and magnetic forces disrupt the delicate balance that has maintained the ring system for at least 100 million years. And the public relations challenge facing NASA and other space agencies involves how to communicate these findings to the public without creating either panic or apathy. Initial press releases about JWST's Saturn observations mentioned interesting thermal features requiring further study, carefully avoiding language that might suggest crisis or danger. But as scientific papers pass through peer review and prepare for publication, the concerning nature of the findings will become public knowledge. How do you explain to a global audience that one of the most familiar and beloved objects in the night sky might be undergoing fundamental transformation? How do you convey scientific uncertainty about timescales and outcomes without either catastrophizing or downplaying the significance of what's being observed? No, the Cassini mission's spectacular conclusion in 2017, when the spacecraft deliberately plunged into Saturn's atmosphere to avoid contaminating potentially habitable moons, now seems tragically premature. If Cassini had remained operational, its comprehensive instrument suite could provide continuous monitoring of the atmospheric anomaly from close range, offering data far superior to what even JWST can obtain from 1.4 billion kilometers away. The decision to end Cassini's mission was driven by planetary protection protocols and the spacecraft's dwindling fuel reserves, both completely reasonable factors. But in hindsight, losing our only Saturn orbiter just 7 years before this unprecedented phenomenon emerged ranks as one of the most unfortunate timing coincidences in the history of space exploration. The prospects for a rapid response mission to Saturn appear dim, given current budgetary and technological constraints. Designing, building, and launching a spacecraft to Saturn requires at least 10 to 12 years under accelerated development timelines, and transit to Saturn takes another 6 to 7 years using conventional propulsion. By the time a new mission could arrive, the phenomenon will have evolved for 16 to 19 years from the current state, potentially long enough to reach whatever crisis point the acceleration is building toward. Nuclear electric propulsion could reduce transit time to 3 to 4 years, but such systems remain in early development and have never been deployed on interplanetary missions. The harsh reality is that humanity will likely observe Saturn's transformation from afar through telescopes rather than with close-up spacecraft observations. The Hubble Space Telescope has been redirected to provide monthly, visible light monitoring of Saturn, tracking changes in the planet's appearance that might correlate with JWST's infrared detections. The September 2024 Hubble images show a faint brightening at Saturn's equator, visible in blue wavelengths, representing a 12% increase in reflected sunlight compared to images from 2022. This visible brightening suggests that the atmospheric anomaly is affecting cloud structures at the altitude where visible sunlight is scattered, approximately 100 kilometers below the levels JWST's infrared observations penetrate. The anomaly is propagating upward through Saturn's atmosphere and reaching levels that will eventually become visible to amateur astronomers observing through backyard telescopes. Within 2 to 3 years, if current trends continue, Saturn's equatorial region will show obvious visible discoloration to observers with moderate aperture telescopes. The planet that has appeared as a serene golden beige sphere with crisp horizontal banding will develop a bright equatorial belt that disrupts its classical appearance. Amateur astronomers worldwide, the same community that has lovingly documented Saturn's changing seasons and storm systems for decades, will witness their favorite planet transforming before their eyes into something unfamiliar and unsettling. The philosophical implications extend beyond astronomy into our understanding of planetary systems as stable, predictable environments. For centuries, we viewed planets as eternal and unchanging on human timescales, with their fundamental characteristics fixed since formation billions of years ago. Saturn has been Saturn throughout human history, the ringed jewel of the solar system, beautiful and comprehensible. The realization that planets can undergo rapid, fundamental transformations within decades, rather than geological eras, challenges our assumptions about planetary permanence. If Saturn can change so dramatically within a human lifetime, what other supposedly stable features of our solar system might be similarly vulnerable to sudden transformation? Earth's climate system provides an unsettling parallel. Our planet's climate has remained within a relatively narrow habitable range for hundreds of millions of years, despite receiving gradually increasing solar radiation as the sun ages. This long-term stability has been attributed to negative feedback mechanisms, the carbonate-silicate cycle, ice albedo effects, and biological regulation that automatically counter perturbations and maintain homeostasis. But the current reality of anthropogenic climate change demonstrates that sufficiently strong forcing can overwhelm these stabilizing feedbacks, pushing the system toward new states. If Earth's climate can be forced into potentially irreversible transitions by human activity, perhaps Saturn's atmosphere can be forced into transitions by its own internal dynamics when critical thresholds are crossed. The detection of similar thermal anomalies on other giant planets has become a research priority following the Saturn discovery. Archival analysis of JWST, observations of Jupiter, Uranus, and Neptune is underway to determine whether comparable phenomena exist elsewhere. Preliminary results show no evidence of similar instabilities on Jupiter or Neptune, but analysis of Uranus data remains incomplete. If the Saturn phenomenon proves unique to that planet, it might result from some specific combination of internal structure, atmospheric composition, or magnetic field configuration that exists only in Saturn. But if similar features are found on other giants, it would suggest we're observing a general mode of giant planet behavior that our theoretical models have completely missed. The discovery has sparked renewed interest in brown dwarfs, objects intermediate in mass between planets and stars that generate substantial internal heat through gravitational contraction. Brown dwarfs show atmospheric phenomena including storms, temperature variations, and magnetic activity, surprisingly similar to what's now being observed on Saturn, just at larger scales and higher energies. Some researchers are beginning to wonder whether the distinction between massive planets like Saturn and small brown dwarfs is less sharp than traditionally assumed. Perhaps planets above a certain mass threshold can spontaneously develop brown dwarf-like atmospheric instabilities, even without having brown dwarf-level internal temperatures. Saturn, with 95 Earth masses, might sit just barely above this threshold. And the long-term fate of Saturn's ring system adds emotional weight to the scientific concern. Those iconic rings, the feature that makes Saturn instantly recognizable even to children, are already known to be temporary on astronomical timescales. Cassini's observations showed the rings are being destroyed by particle infall at a rate that will eliminate them within 100 to 300 million years. But that timeline assumed normal atmospheric conditions. If the thermal anomaly significantly enhances the rate of ring particle infall, the rings could disappear within mere thousands of years, timescales short enough that future human civilizations might witness their complete loss. The idea that humanity might be living during the final centuries when Saturn possesses its magnificent rings carries a melancholic poignancy that transcends pure science. And the international cooperation triggered by this discovery demonstrates both the best of the scientific community and its limitations. Researchers from 17 countries have contributed observations, modeling, and analysis, sharing data openly and collaborating across institutional and national boundaries. Yet, the actual response capability remains constrained by the harsh realities of space exploration budgets and physics. All the brilliant minds and sophisticated instruments in the world cannot change the fact that we are 1.4 billion kilometers away from the phenomenon we're trying to understand, limited to remote observations that capture only indirect signatures of the underlying processes. We are planetary physicians trying to diagnose a patient we can examine only through long-distance imaging, unable to conduct the direct measurements that would provide definitive answers. The younger generation of planetary scientists faces a strange burden. They may spend their entire careers studying Saturn's transformation, watching the planet evolve in real time, rather than reconstructing its history from ancient geological records. Graduate students beginning Saturn research in 2024 could still be actively observing and modeling the phenomenon when they retire in the 2060s, having devoted their professional lives to documenting a single planetary event. This represents an unprecedented opportunity for sustained observation, of planetary evolution, but also an unsettling reminder that we're witnessing changes we cannot control or reverse. The question that haunts every late-night discussion among researchers is simply, why now? Saturn has existed for 4.6 billion years. Humans have observed it through telescopes for 400 years, and spacecraft have studied it intensively for 40 years. In all that time, no hint of this phenomenon appeared. What triggered its emergence in 2024 rather than 2024 BCE or 2024 CE plus a million years? Is the timing purely coincidental, or does it represent a deterministic outcome of Saturn's evolution reaching some critical threshold after billions of years of gradual change? And most disturbingly, if it happened now for the first time, what prevents similar first-time events from occurring on other planets or Earth itself? The data continues accumulating. JWST conducts weekly monitoring observations, building a timeline of the anomaly's evolution with unprecedented precision. Ground-based infrared facilities contribute complementary observations when Saturn's position allows. Radio telescopes listen for emissions that might provide clues about magnetic field changes. And researchers around the world run simulations, develop theories, and debate interpretations, trying to understand what they're witnessing. But beneath the scientific activity lies an undercurrent of fear that few are willing to voice publicly. We are watching something we do not understand, cannot control, and may not be able to predict. We are witnessing a planet, a massive, ancient world that has existed essentially unchanged throughout human history, undergo a transformation whose ultimate outcome remains unknown. We are confronted with the uncomfortable reality that the universe is not as stable, not as predictable, and not as safe as we'd like to believe. The serene golden planet with beautiful rings is changing into something else, and we can only watch as the transformation unfolds across the vast gulf of interplanetary space, hoping that when it concludes, in years or decades or centuries, we will have learned something profound about how planets work, why stability sometimes fails, and what it means to witness cosmic-scale changes during the brief span of human observation. The universe is not required to make sense to us. It is not obligated to change slowly enough for our comfort. It simply is. Following physical laws, we're still learning to understand. Producing phenomena, we're still learning to recognize. What James Webb detected in Saturn's atmosphere is truly terrifying, not because it threatens humanity directly, but because it reveals how little we truly understand about the worlds we've spent centuries studying, and how suddenly the familiar can transform into the unknown. The final, most unsettling thought is this: we are early in our planetary observation history. We've monitored these worlds with sophisticated instruments for mere decades. What other transformations might be building slowly on other planets, accumulating energy, and approaching thresholds we cannot yet detect? What might Jupiter or Neptune or even Earth itself be preparing to reveal? The cosmos keeps its secrets until it chooses to show them. Saturn is speaking now, telling us something we've never heard before. Whether we're wise enough to learn the lesson before the transformation reaches its conclusion remains to be seen. The data comes in, the temperatures rise, the acceleration continues, and we watch from our small blue planet as the ringed jewel of the solar system becomes something we no longer recognize.